So welcome everyone. So it's my pleasure to introduce Professor Michael Filaseta. So he's from University of South Carolina, and today he's going to talk about on a dense universal Hilbert set. So Michael, please.
Thank you. I appreciate the chance to be able to talk to you because it's been never like I talked in TIFRA once, I guess, but I haven't talked in New Delhi yet.
Yeah, just one. So if anyone wants to ask any question, please write in the chat box, and so I will act as a mediator between you and Michael for the questions. Okay, please.
And right now I can see the chat box, so hopefully I can see it as well. So this is joint work with a former student of mine, Robert Wilcox, which got published last year. I'm going to begin by talking about historically where this subject comes from, which goes back to a paper of Hilbert's in 1892. And the main goal of his paper was to show that for each positive integer n, there's a polynomial with rational coefficients whose Galois group, when you join all of its roots, is going to be the symmetric group on n letters. And also to show the same thing is true for the alternating group. So for each positive integer n, you can find a polynomial whose associated Galois group is the alternating group on n letters. And the very basic idea is to find an irreducible polynomial in two variables over the rationals whose Galois group, when you view this as a polynomial in x with coefficients from q of y, is Sn, or An if you're trying to do the alternating group. And then to show that there's choices for the rational values for y, such that when you plug in that rational values for y, you get this to have Galois group either Sn or A sub n. So how to make the right choices? Well, actually, he doesn't even go into that. He just shows that you can find y like this, and we'll see, hopefully, some idea where that comes from, at least from my point of view. So just to give this some explicitness to it, here's an example of a polynomial you can take in two variables.
Yeah, Michael, we can't see your next slide. I mean, when you say here's an example, we can't see the slides.
You can't see the slide right now?
Yeah, I mean, we can just see the front page, but nothing else. Just your.
Oh. Maybe I lost connection. It doesn't say my connection's lost in this end.
Yeah, we still can see that one. So earlier okay, yeah. So
I went out of it. Is it off of it right now?
Yeah, so now it's off, so you can try now.
Going back in. Do you see the first slide still, or?
Yeah, just the first slide.
Did it go blank?
No, it's not blank, just the title page. So basically.
Still the title page. You're still seeing the title page?
Yeah, we still see your title page.
Okay, let me see if I can stop sharing, and I'm just going to do it from my computer. Let's see, how do I stop the sharing? Sorry. Okay. Let's try to go from my computer.
Yeah, sure.
And to do that, I share the screen, I guess. Is that what I do?
Yeah, sure. Please share the screen.
And how do I do that? I'm used to using my iPad.
Yeah, so from the iPad, actually, in the first time you were showing, so we could see the other pages. But, yeah.
Share desktop one, is that what I do? Probably. Let's try that.
Yeah.
Can you see my desktop now?
Yeah, yes, I can see. Yeah, I can see.
Let me make sure I'm getting the right one.
Yeah. Yeah, so now I think we can see, yes.
Okay, you can see it now?
Yeah.
Okay. There's probably a better way I can do the pointer, but I'll go ahead and use this arrow. I have your faces off to my side. You can see the full screen though?
Yeah, I can see the full screen.
Okay, okay. So change pages?
Yes, yeah, now it's, yeah. Okay, now it's.
So this was Hilbert's irreducibility theorem. I'm sorry, this is Hilbert's theorem he had again, that for each positive integer n, he can find a polynomial over the rationals whose associated Galois group was either the symmetric group on n letters or the alternating group on n letters. And again, the idea is to find a polynomial in two variables, f of x, y, with rational coefficients, such that the Galois group of this polynomial as a polynomial in x with coefficients from q of y is Sn, or An if you're trying to prove something for the alternating group. And then to show that you can find rational choices for y so that the polynomial f of x with those y values has Galois group Sn, or A sub n over the rationals. So that's the rough idea of what he does. And I was giving this explicit example of an f of xt where the polynomial xdn minus x plus t actually has Galois group Sn as a polynomial in x with coefficients from q of t. And this is not exactly the choice he makes, because I went to his paper to see, well, what did he take for a polynomial? And he's actually kind of vague. So what he says is that you can take instead a g of x plus t, as long as g of x plus t has these properties that the zeros of g prime of x have multiplicity 1, and if you plug in any of those zeros into g of x, you get different values. So I just took xdn minus x for my g of x just to make it something simple. And then he goes on to show there's infinitely many choices then for t that are rational numbers, so that the Galois group of this is Sn over the rationals, so as a polynomial in x. So that's the rough idea of what he does, and there's an explicit polynomial he does it with. Serre later showed that one could take t0 equal to minus 1 for all n. So if I take this t to be t0 here, this t to be minus 1, then this has Galois group Sn for each n. Now, Hilbert's doing something a little bit more. He's showing there's definitely many polynomials like this that one can take, but Serre pointed out that one could do that. For the alternating group, I use Serre's choice here, a little bit easier than Hilbert's, but he mentioned this choice for an f of xt. You can see it depends on the degree here, and this is when n is even. For n being odd, you would take a different choice. But Hilbert takes g of x plus or minus t squared, again being somewhat vague, but saying just take any g of x like this, where g of 0 is 0, and the derivative has a certain form here. And you can see that. So Hilbert had something that was rather general without being specific, but that would be a specific example one could take up above. And as I said, you can do something similar when n is odd for the alternating group, but I won't write that down. It's a little bit more difficult. So this is back where we were. And one part of this that Hilbert discusses is that you need a polynomial to be irreducible to get the right Galois group. And in a sense, what he does is also proves that if f of xy is irreducible over the rationals as a polynomial in two variables, then there's infinitely many choices for y, so that this is irreducible as a polynomial in one variable in q bracket x. So these choices for y are rational numbers. But he actually goes into this quite a bit and doesn't quite go this far. So this is about as general as you can get with this irreducibility theorem of his, that you have if m different polynomials here, in all these variables, r plus s variables. And we can find if these are each irreducible over the rationals in these r plus s variables, then you can find rational choices for the y variables here so that the polynomials are irreducible over the rationals when you plug in those rational values for y. And just to clarify, I cut and pasted this. I didn't really tear it out of his paper, but I did cut and paste this from his paper. So it's basically saying if you have a polynomial in several variables, he's calling these the variables and these parameters, but it's irreducible in all of these variables, that you can find infinitely many values for rational values for these, what he's calling parameters, so that the polynomial remains irreducible in the other variables. So he does do that variation. He also does a variation where you have a number of polynomials in two variables. And again, each of them irreducible in these two variables over the rationals, that you can find choices for t, rational choices for t, so that all of these, each of these is irreducible over the rationals when you plug in these rational numbers for t. So those were variations of his irreducibility theorem that he wrote down. So I may want to concentrate on this rather than the Galois group question, which I will come back to the Galois group in a little bit. So comments and improvements on this. Hilbert's original proof was ineffective. He didn't say how to find these rational numbers y, just that they existed. And now we know we can find integers y, in fact, and that, in fact, most integers y satisfy that, when I say good, when you plug these in here, these are all irreducible. So most integers y will have that property. The density of these is 1. That's an asymptotic density. And then it's also been shown that there's arithmetic progressions, such that if you take any y from these arithmetic progressions, you're going to get a good choice for, meaning that, again, when you plug in those y's, you're going to get something where all these are irreducible. The next result I took from a paper by Siegel and Zannier. It's the case where there's only two variables. So when I say y sub 1 here, there's only one y, and there's only one x. And so it's a polynomial in two variables, but you have m of them. So m polynomials like before. We have the degrees, the maximum degrees of these in terms of x and y. And the height here is the maximum of the absolute values of the coefficients. So you do that for each of these. Take that to be h. And then you get this bound on the first solution as an integer. So you can find an integer between a positive integer, so an integer between 1 and this, where you can use so that all of these polynomials that we have up here, but it's only two variables, x and y, are irreducible at the same time. So that makes Hilbert's irreducibility theorem, at least in this case, effective, because you just have to try all these different values for y, and you have a specific upper bound that you need to go to. So I wanted to mention that the Hilbert's irreducibility theorem was a part of Weyl's original proof of Fermat's last theorem, so it also comes up there. So this is a fairly important theorem. So roughly, an irreducible polynomial in several variables has infinitely many specifications when you take specializations, I guess I should say the way I wrote it here, when you take the sum of the variables, pre-selected variables, to be rational numbers, any ones you want, you can make it irreducible in the remaining variables. So that's the basic idea. So I'm just going to be looking at, for the rest of this talk, one polynomial in two variables. So it's irreducible over the rationals, and I want the degree in x to be at least 1. So when I plug in y, it has a chance to be irreducible. So here's an example of Hilbert's irreducibility theorem. We have two polynomials that are relatively prime in z bracket x and not constants. And we go ahead and look at this polynomial is f of x plus y g of x. And by Hilbert's irreducibility theorem, we can find infinitely many integers k for y that make this irreducible in x. So that you can think of as a generalization of Dirichlet's theorem. Instead of numbers here, we have polynomials, and we're making it irreducible rather than saying prime. So in fact, you could think of this as saying that it's irreducible over the integers, and that would allow for Dirichlet's theorem as well. Another example I wanted to explain, because it's kind of nice, is the following: that you take a polynomial f of x in z bracket x, and suppose that you know that when n is large, an absolute value, that f of n is a square. Then Hilbert's irreducibility theorem implies that f of x itself has to be a square of a polynomial. So why is that? So it's really the contrapositive we want to think of in Hilbert's irreducibility theorem, which is telling us if we have a polynomial in two variables, and there's only finally many choices, say for integers y, such that the polynomial in two variables is irreducible, then that would mean from Hilbert's irreducibility theorem that the polynomial in two variables is reducible. It's not irreducible. So that's the contrapositive. So the polynomial I want to start with is x squared minus f of y. And notice that for almost all the integers, except for finitely many, once the y is big and you plug it in here, you're going to get a square, because that's the condition on the example. And if this is a square, then this is reducible. It factors. X squared minus a square will factor. So it'll be reducible whenever y is large, a large integer, which means, again, by the contrapositive of Hilbert's irreducibility theorem, this has to be reducible. And then you just have to think of what that means to be reducible. If you know Capelli's theorem, it's an immediate consequence that f of y is a square. But even if you don't, you just try factoring this. If it's reducible, it's x plus something times x plus something, because it's quadratic here. And you don't want an x term, so one of the somethings has to be minus the other one. So you have something like x plus g of y times x minus g of y. And so you're going to get f of y has to be g of y squared.
Excuse me?
So you have, yeah, go ahead.
Excuse me. In the example, n every sufficiently large n? For every sufficiently large n?
Yeah, every sufficiently large n, either positive or negative. So every sufficiently large n an absolute value.
Okay, thanks.
And as I mentioned, it's known that in an asymptotic sense, so when I say almost all here, it's not an algebraic sense, it's more of an analytic sense. The way number theorists talk, almost all means asymptotically, almost all integers have this property that this will be irreducible when I plug in and y equals y0. Again, with these conditions. So specifically what this means is that if I count the number of integers with absolute value less than or equal to some capital Y here, where this is reducible, so where it's not irreducible, then you want to say there's not very many of them. And this notation, which equals a little over y, means that when I take this expression here and divide by y, as y goes off to infinity, this goes to 0. So the number of cases where you have reducibility is going to be going to 0 asymptotically. So again, the density is going to 0. So it's really saying the density of y's that make this reducible is 0. If you use Siegel's lemma, which I'll talk about shortly, you can say a lot more. You can actually say it's less than or equal to the square root, well, less than or equal to a constant times the square root of y, square root of capital Y on the right-hand side. So it's less than or equal to a constant times the square root of y, and that constant will depend on the f. So that would come out of Siegel's lemma, so you can get even something even stronger. And just to, so this is the main topic I want to talk about is, well, in some sense, but a universal Hilbert set is an infinite set, subset of the integers, having the property that for every polynomial f of x, y in z bracket x, y, which is irreducible in the two variables, and satisfies the degree, again, of f with respect to x is at least 1, there's going to be finally many choices of integers in S, such that this polynomial is irreducible in Q bracket X. So to emphasize here, the important parts here are there's only finitely many y0 and s with this being reducible. So that would be like replacing that constant times the square root of y I just mentioned with a constant. The constant, again, will depend on f, but you can say then that there's just finitely many if you restrict the y you're looking at to the set S.
So, Michael, here I have one question. So, so this set doesn't depend on the polynomial, so it's independent of this polynomials f, right?
Yes. So I just put that bullet up, and the other important thing here is that this set is fixed; it's independent of f.
Okay, thank you.
Yeah. So yeah, I'll be talking about that set for a little bit. So we'll get the information, some more information on this set. But this set is so both of those are very important aspects. That the set doesn't depend on f, and we just have finitely many y's in S instead of infinitely many. So if I look at the example x squared minus y, you can see that z itself can't be S because there's infinitely many choices for y by taking y to be a square here, where this is reducible. And so we want only finitely many choices for y in S, finitely many, where it's reducible. So you can't take S to be z, right? So in fact, S can't have infinitely many squares because then there'll be infinitely many choices for y here where this is reducible. So S can only have finitely many squares. And if you look at x cubed minus y, S can only have finitely many cubes then as well, and so on. So for each k, S can have only finitely many kth powers. So that's some restriction on S. And let me mention that this was first shown to exist, that there are sets like this, infinite sets S like this, in a paper by Gilmore and Robinson in 1955. It took about 26 years later for an example to come by. And this was an example that came from, well, it came from 1981, 1981, but also 1983 there, but was found published in 1981, and it gives a specific example of a universal Hilbert set, so by Spencer. Some other perhaps nicer examples came along. So this is one by Corvalle and Zannier, Debs and Zannier, Bilu, and Zannier. Notice I did not put these in chronological order. This was the oldest. These were more recent, and then this was the next oldest down here. But what I did was to put these in order of how many things are in these sets. And this set is growing very fast, the ends here, so in some sense it's the thinnest of the sets. There's not very many things in this set compared to this set, and then this one has maybe a little bit more than this one, still growing exponentially. But this one's more like cubic, so growing a bit slower. And this one is around n log squared n. So this is almost linear. So the two papers in the middle here, Debs and Zannier and Bilu, actually commented in their papers that it's possible to find universal Hilbert sets with asymptotic density 1 in the integers. So it is possible to get a set S which has almost every integer in it. So that's can be a fairly big set then. The result with my student is a little bit stronger statement than that. First, we can make it explicit, which they didn't do, but we can say a very explicit set S here that has the property that if you look at the things that are not in S up to X, it's bounded by X over a power of log X. So it's a little bit better than saying little o of X, which would be what asymptotic density 1 means for irreducibility. It's less than a constant, this means less than a constant times X over log X to the delta, where this is delta. So again, the less than is like a big O, it means it's less than a constant times X over log X to the delta. So all these sets S also have the property that if you look at the Galois group associated with f of x, y over q adjoin y, And if that's G, then for all but finally many y naught in S, the polynomial f of x y naught has Galois group G over Q. It's not true if it's irreducible, it necessarily has this Galois group, but basically the same arguments work for all these S's to show this result. So the classical idea behind universal Hilbert sets is the following, that if you want to determine whether f of x y naught has Galois group G over Q, where G is the same thing I talked about up here, so it's a Galois group of f of x y over Q of y. If you want to know whether, when you specify what y is, this has Galois group G over Q, you look at what's called the resolvents of the maximal subgroups of G, and you get these polynomials f of x, y for those resolvents. I'm sorry, look at resolvents, there are polynomials in two variables, x and y. And in order for that to have Galois group G, you're going to need the resolvents to have the property that for the choice of y, you have y naught, there's a rational value of x that makes that 0. So in other words, if you think of the resolvent as being, let's say, g of xy, g of xy, when we plug in y naught, is going to have a rational root. So g of xy equals 0 is going to have a rational point on it. The curve g of xy equals 0 has a rational point. And you want that to hold for each of these resolvents that you get, and then you'll be able to say that this has Galois group G. So it boils down to having some curves and looking at rational points on these curves. And a nice description of how to get Galois groups this way, at least I found it very nice to look at, was this paper by Stoddard. It's a somewhat classical paper now for how to calculate Galois groups. If you look at how people calculate Galois groups now, you'll see references to this. So Magma makes use of this, for example, to compute Galois groups. But it's been refined, but it's a classical paper for that subject. And he describes very nicely how to get the Galois groups, what the Galois groups are by looking at these resolvents of the maximal subgroups of G. I was trying to give an argument for Hilbert's irreducibility theorem that didn't talk about Galois groups. So that's why I wanted to do this a different way. And so these curves that you get by looking at resolvents, I wanted to avoid, to give maybe a more simple explanation of how Hilbert's irreducibility theorem comes from Siegel's lemma. And I wanted to avoid somehow using these curves here. So I am going to find curves, but not by using resolvents of f of x, y. So we'll talk about that in a little bit. In fact, I want to go ahead and do an example. And this example will give an idea of what I had in mind here. Check my time here. So this example, do I have a question or?
Please carry on.
Oh, no, I was checking my time on my iPad. So this polynomial in two variables we want to show is usually irreducible. It's only reducible when y0, when you plug in y equals y0, or y0 is one of these 9 values. So I'm going to go ahead and explain how to show this. And it'll give you a rough idea what I have in mind in general for getting at these curves. So let's suppose this has a factor. I made it monic to make it a little bit easier. So if it has a factor, if it's reducible, it's going to have a factor that's either linear or quadratic. So I'm going to look at the possibility that it has a factor g of x, where g of x is linear or quadratic. And since, again, f is going to be monic, I can take g to be monic. So there's two possibilities for what g of x can look like. It can either look like x minus a for some integer a, or it can look like a quadratic, x squared plus ax plus b. Now I want to look at those two cases and see what happens. When can x minus a be a factor of f of x, y when you plug in some integer for y? And the same thing with when can it be divisible by this x squared plus ax plus b? So for this, if this f of x, y is divisible by g of x when we plug in y, then that means that a has to be a root. So I just have to plug in a and see if I get 0. So I'm going to end up with this when I plug in a. fourth here. Let's see, did I rearrange things here? Plugging in A, I have a to the fourth y plus 8 times a. So it looks like maybe, I took I made it monic by putting the y squared minus y on the other side. So I set this equal to 0 and brought everything on the other side. And this is the quadratic I get when I plug in A. So you might be able to tell this is a curve. I mean, it is obviously a curve in y and a, but you might be able to tell me more about it. But what I went ahead and did here is to think of this as being a quadratic in y. So remember, we have a being an integer here. We're plugging in an integer y, and we're saying this has to be true. So that means that whatever a is, this is a quadratic in y that has an integer root to it. So in particular, it has a rational root. So if it has a rational root, the discriminant has to be a square of a rational number. So in other words, when I take this squared, minus 4 times this, I'm going to get a rational square. So I went ahead and calculated the discriminant here, 1 minus a squared minus 4 times this, and multiply that out. And I want to set that equal to a square, which I'm going to call w squared. But a is an integer here. W is a rational number. When I square a rational number, I'm getting an integer. That actually means that w has to be an integer as well. So I have an integer solutions to this equation, and this is a elliptic curve. So this is a form for an elliptic curve, and you can rewrite it in Weierstrass form, and we can find the integer points on this curve. But you have to be a little bit careful, and the reason is if I want to get these integer points again, like I use Sage to do this at some point, you need to write it in Weierstrass form, and the catch here is that integer points for this curve don't correspond to integer points on our Weierstrass form when we write it in Weierstrass form. So it's going to be some rational points there that we need to look at, and so it can be done this way, but you have to be careful. It's not just rewrite it in Weierstrass form and look at the integer points. The integer points on this Weierstrass form will not necessarily be the integer points you want here. So there's an easier way to do this, and the easier way is the following. And my colleague Agnian Trifonov pointed this out to me. You can multiply both sides here by 16, and the reason for doing that you'll see in a second. So I have 4w squared here, and then 64a to the fourth, and so on. But once I multiply by 16, you can combine these two terms by completing the square, and you get the 8a squared plus 1 squared plus the 480a plus 15. So the idea is that the difference between two squares when a and w are big here is not going to be this small. So we go ahead and analyze this. If a is an integer, we can see a is an integer, so we can see that this is not 0 because if you solve here for a, of course, you're not getting an integer. So either 480a plus 15 is bigger than 0 or it's less than 0. So I'm going to look at those two cases. They're both fairly quick once you look at them. If it's greater than 0, that means a is greater than minus 15 over 480, and so a is going to be greater than or equal to 0. And this equation is just coming from the first equation I had up here. Just put them in the opposite order. But what I'm trying to say here is that I know that it's more than this squared because this is positive over here. So it's more than 8a squared plus 1 squared. And I know it's a multiple of 4 squared. So it has to be at least 8a squared plus 4 squared. And that's what I have here, 8a squared plus 4 squared. So that's where this is coming from. The 16 and the 64a to the fourth cancel from both sides. And I bring the 16a squared, I'm going to have a 48a squared is less than or equal to 480a. Sorry, didn't mean to do that yet. Be a little careful here. So when I cancel the 64a to the fourth and the 16, again, I bring the 16a squared over, I have 48a squared is less than or equal to 480a. A equals 0 is here. If a is positive, then I'm going to have, by dividing by 48a, that a is less than or equal to 10. So a on this side will be less than or equal to 10 on this side. So that tells me a has to be between 0 and 10 there. And yeah, just do something similar for the other one when it's less than 0. Again, this is just the same thing as this equation we started with here. I know now that it's a multiple of 4 squared, but it's less than this, because this is negative now. And so I have this minus something. So 8a squared is a possibility. It's less than this. And if I square it, it's divisible by 4 before I square it. And I'm going to get 64a to the 4th then. But can 4w squared equal 64a to the 4th? So can it be 8a squared squared? And the answer is no, because 8a squared squared would be 64a to the 4th. These would cancel. And you would have this being 0. And if you just solve that quadratic, it turns out to be the solutions are minus 15 plus or minus the square root of 14. So they're not integers. So we don't have to worry about the case where this is where 4w squared is 8a squared squared. So the next multiple of 4 below that would be the 8a squared minus 4 squared, which is what I put here. Again, the 16 and 64a to the 4th cancel. I bring the 64a to the squared over here. I'll have 80a squared, bring this over. 80a squared is less than or equal to minus 480a. You want to divide by 80a, but keep in mind a is less than 0 because this is less than 0. So it changes the sign. And so you're going to end up getting that a is greater than or equal to minus 6 when you do that. So we end up with a being between minus 6 and 10. And now that we have that, we just go up here where we have an equation in y and a, and we just try each of the values of a and see what we get for y. We want y to be an integer, and you can plug those into here and see which one gives us the linear factor. So that takes care of the linear case. Again, when we do that, we get these y's. So again, that just came from plugging in these a's into here and seeing what happens with y. There's 8 values of y there. For example, when y equals 105, if I plug it into our original polynomial in x and y, I get this, and I factor it. X minus 10 turns out to be a factor. So that would be the case with a equal to 10. For case 2, where I have a quadratic, what I'm going to do is think of this as like I'm plugging in a y naught here, so think of this as a polynomial in just x, and divide it by g of x, and look at what the remainder is. So if you just do the formal division, just take g of x, divide it into here, this is what you'll get for your remainder. So the remainder is going to have a coefficient for x and a constant term because we're dividing by a quadratic. And what we're interested in is g of x dividing f of x, y. So we want this remainder to be 0, which means both of these coefficients have to be 0. So we end up with 2 polynomial equations equal to 0. And we have 3 variables, a, b, and y. And what we'd like to do is to eliminate one of them and make an equation in just 2 variables so we have a curve that we can look at. So that's the idea. You can see it's easy to solve for b or y in terms of a and the other variable here. So I solve for b, I can plug it into here, or solve for y and plug it into here. But in general, these might not have be linear in any of the variables. And so I wanted to explain what you would do if they weren't linear in any of the variables. And it's still possible to say something here. The way you look at this, or one way to look at this, you can look at it as a Grubner basis if you know what that is. But equivalently, another way to look at this is you think of a and y as being fixed, and then or any 2 variables doesn't make any difference. A and y is being fixed, and then you have 2 equations with a common root in b. So if a and y are fixed, you're saying there's some b that makes this 0, and there's some b that makes this 0. So you have 2 polynomials in b that are equal to 0, which means they have a common root. So the resultant of these 2 polynomials, where b is the variable, has to be 0. The resultant you can write in terms of, it's going to be in terms of the coefficients of these polynomials where b is the variable. And so it's not going to involve b, it's just going to involve a and y. And you end up with this. This would be the exact same thing you would get if you solved for b or y here and plugged it into here. But, well, I guess if you solved for b and plugged it into here. So you get this polynomial in 2 variables equal to 0. And we want to know now the integer points for a and y here, really what y can be here. Well, again, we have a quadratic in y, and y is an integer, so a rational number. So the this discriminant is going to have to be a square. If you wanted to avoid some of this, you can say, well, Siegel's lemma, this has genus greater than or equal to 1 if you check, and it's going to have finitely many points, but they won't tell you what the points are. But if I look at the discriminant of this as a polynomial, this is a quadratic in y, look at the discriminant, it has to be a rational square. So again, that's going to be an integer square then, but w squared has to equal this. Now, you can see a negative sign here. That's coming from looking at the minus 4ac part. So this is part of the a and the ax squared plus bx plus c. You have a minus 4a squared. This is part of the c. You're going to be multiplying these together times the negative 4. So the minus 4ac, that's going to give you this. So that's where that's coming from. You do have that negative thing there. But you go ahead and calculate the discriminant of this quadratic. This is what you get. It happens to factor fairly nicely. If a is greater than 2 here, you can see everything is positive here except for this minus sign here. So you're going to have a negative number, and then it's not going to equal a rational number squared. So a has to be less than or equal to 2. If a is less than minus 2, this is negative, and this is negative, this is positive. So it's still going to be negative again if a is less than minus 2. And again, that won't be a rational number squared or an integer squared, so we don't have to worry about those. We only have to worry about a between minus 2 and 2. You plug in each of those into this equation in y and a, solve for y, and you get what y can be, and you get minus 3, 0, and 7. And 7 is the only one of these three that didn't occur before. And if I plug in 7, you can see this is what I get when I plug it into f of xy up here, and it factors, and you have this factorization of two quadratics. But combining these, we have that the only way f of xy can be reducible when we plug in a y is if a y is one of these 9 different values here, and that finishes this example. So the main idea for getting these curves is to use resultants to get rid of variables. Are there any questions before I go on?
Yeah, so far there is no question, I think, from the chat. So, but if anyone wants to ask, please feel free to ask. I think please go ahead. At the end, people may ask.
So this is the main result again. I wanted to comment that this is it doesn't have a lot of elements in it up to 10 to the 6. So less than half the integers up to 10 to the 6 are actually in S. So it's not small yet, but you can see that as x gets large, it has to be getting small compared to x. But even to make the situation worse, let me point out that log x is so small and delta is so small that you actually take any x in this range, this expression right here is bigger than x over 2. So it's not small yet, even if you go all the way up to here. I don't know what the constant is here, less than a constant times this x over 2. But you see it takes a while for this to get small.
So Michael, here I have a quick question. So how do you get, like, so up to 10 power 6, you have 4,60,000. Yeah,
I haven't told you what S is yet. Sorry, that's coming up. I will be telling you what S is.
Okay. Thank you.
Let me mention that delta is the Erdős, is called the Erdős-Tannenbaum Ford constant. And Erdős first came up in work of Erdős, where he showed that the number of distinct integers in an n by n multiplication table is equal to n squared over log n to the power delta plus a little over 1. So something here that's going to 0 with n. And it'll come up in Ford's work that I'm going to describe a little bit later. So what's S? So it's not nice like the other S's we were talking about. So I wanted to forewarn you. So what's this set? So I'm looking at j greater than or equal to 3. These k and l prime. And I'm taking m in this what's called a dyadic interval. It's an interval going from 2 to j to 2 to j plus 1. And as j varies, you can see, well, j is greater than or equal to 3, so it starts out at 8. But every integer is going to be in an interval like this that has absolute value bigger than 8. So I'm getting every integer this way if I take the union of the j's. But for each m in an interval like this, and think maybe of this as being a big interval, so j is large, I want to look at a linear combination of m. And I'm going to call this a small linear combination of m because I want L and L prime to be small. And I'll explain what small means in a second. But I'm going to think of L and L prime being small compared to m here. And k is also going to be small. So I'm looking at small linear combinations of M that have no divisors in this interval that's around the kth root of M. So if I take the kth root of M here, it's going to be around this. Okay, so small linear combinations of M have no divisor around the kth root of M for k small. And what I want to do is I want to look at k, L, and L prime that satisfy all these together. So I'm going to be taking an intersection of these sets over k, L, and L prime. So every small linear combination of M will have no divisor in around a kth root of M for every small k. So what does small mean? So this is going to be a bound I'm going to put on the L, L prime, and k. So they're going to be that small. So they're fairly small compared to what M is. M is around 2 to the j, and you can see that these are very, very, very small compared to what M will be. So again, I have an intersection. I want k to be at least 2, so I'm really talking about some root, kth root of this. And again, k, L, and L prime are really small. I'm taking an intersection. So I'm looking at things in my set that are bigger than the union here. So it's bigger than 8. But each of these M's have the property that every small linear combination in M has no divisor around the kth root of M, where k is small. So that's what the set looks like. It's explicit, not nice, but you can compute what's in S and what's not in S, and that's what I did. So here's the result again. There are a couple things to explain here. Well, why is this a universal Hilbert set? And where's this estimate x over log x to the delta coming from? So let me give you the explanation for where this is coming from first, the upper bound. But notice it's counting M not in S. So what does it mean to be not in this set? So that means M is going to have the property that some small linear combination of M has a divisor inside this for some small k. Okay, has divisor near the kth root of M for some small k. So if I'm trying to estimate things that are not in S, I use the following theorem. This is due to Kevin Ford. And you can see it's counting the number of positive integers which have a divisor in an interval. So I want to think about taking n near x in this description here, and y and z will be around the kth root of x, basically, but they're going to be very close. You know, the difference between y and z wasn't very much. They were very close to make this an interval close to the kth root of x. That means this is going to be very close to 1. So if you actually compute what u is in this, something close to 1, we're subtracting 1, it turns out to be around 1 over log x. So you can see you're going to have 1 over log x to the delta here. Remind you, this is what we're looking for. And you're going to, this x is going to become a capital, that's the same x. So you're going to have x over log x to the delta, and you actually get an extra log x to the 3/2 in the denominator here. So that we could have put there. So you're getting this estimate coming out of this estimate of Kevin Ford's. I'm not giving you the details, but that's where it's coming from. If you calculate what u is, it's around 1 over log x, and you're going to get this. So that's a rough idea where it's coming from. For Siegel's lemma, that's what we're going to use for showing this as a Hilbert set, universal Hilbert set. And I wrote Siegel's lemma this way. So usually you see Siegel's lemma saying you have a polynomial f of xy and z bracket xy that's irreducible over the complexes. If the genus is greater than or equal to 1, then there's finitely many points on the curve where you get 0 here. So here I'm saying there's definitely many points on the curve. Then that means it has to have genus 0, and what the rest of this is describing what it means to have genus 0. So to have genus 0, basically these rational points are going to come from looking, you can write them as a, you can find rational function here, where u2 and v2 here are polynomials in T. You can find a rational function so that all the rational points, or all but finally many, are coming from looking at u2 of T over v2 of T for y, and something similar for x, and the T is rational. So that's what it would mean to have genus 0. And we'll come back to that. So here's the idea for the proof. I take my polynomial f of xy, so we have this f of xy here. I assume it's reducible. It's going to have a factor degree k, where k is less than or equal to n over 2, just like we had before with the 4th degree polynomial having a factor degree less than or equal to 2. So it has a factor degree less than or equal to n over 2. I want to take my polynomial after I plug in y0. Imagine taking this polynomial and dividing it by a kth degree polynomial, where I don't know what the coefficients are, but I'll call them h sub 0 through h sub k minus 1. Everything's monic because I'm doing the easy case where f is monic. After you divide, you get a remainder. We're dividing by a polynomial degree k, so we get this remainder will have degree k minus 1. These coefficients will be in terms of the unknowns when you do the division. They will depend on the h's here, the hj's, as well as on y. So we get these polynomials in k plus 1 variables. And if the remainder is going to be 0, so this is the polynomial is divisible by h of x, we want each of the coefficients to be 0. So saying there's a y0 in here, such that f of x y0 has a factor of degree k, is the same thing as saying there's a k tuple for the h's, such that when I plug it, that k tuple h's with y0, I'm getting 0 for each of those. So we want to show that this holds for only finitely many y's in my set S, my universal Hilbert set. To do, well, I just rewrote this way. It's not really saying much difference. We have a bunch of equations talking about this variety, just talks about you're looking at when these points where these are all 0, and I'm just saying the same thing I wrote in this bullet basically there. So the basic idea is if you have a linear system of equations and k unknowns, we typically expect us to be able to express a linear system with k equations and k plus 1 unknowns, sorry. K plus 1 is on my site here. K equations and k plus 1 unknowns, we can typically expect to be able to write, say, each of the h sub j's in terms of y. But they're not linear. And so if you use resultants instead, or a Grubner basis, boils down to the same thing, you'll be able to reduce the problem to instead not h of j being in terms of y, but a polynomial in h of j y equal to 0. So you end up with curves, one for each j here, where the curve is some polynomial in h of j and y equal to 0. Now you can hope that Siegel's lemma applies to just even one of these curves. That would tell you that, because you need all of them to be true, be satisfied at the same time. That would give you that if one of them had genus greater than or equal to 1, there's only finitely many y we need to worry about, and that would be good. But if the genus is 0, that causes more problems. And I really only have really 2 new slides to go. So one is this, this sort of summarizes what happens in the genus 0 case. I use that if f of x and g of x are relatively prime polynomials. I'll describe in a little bit where they're coming from. And you look at this f of x plus y g of x here. It has a linear, if it has a linear factor, that's going to occur for only finitely many y's in S. Okay, so that's a lemma that requires some proof. That's really the guts are. I won't go through lemma 2. I'll sort of summarize that in a second in a different way. But if I look back at what the importance of this, so I have f of x plus y g of x here. It doesn't have a linear factor unless for very many y's in S here. I go back some slides here to what we had before for Siegel's lemma. This f of x, y, and this Siegel's lemma that I want to use is the curve we just got in h sub j and y. So really, this is h sub j and y here. So we're taking one of these curves we found where f of h sub j, y has to be 0, and looking at points there. And what this is saying is that the y will have to be able to be written as a rational function like this, u2 over v2. And if I rewrite that, that's going to be u2 minus v2y is equal to 0. So that corresponds to what we were looking at in this lemma. So this is u2 of t. This is minus v2 of t. And we have this linear combination then with y. So u2 of t minus y v2 of t is equal to 0. And this is telling us that, well, when I plug in y being an integer, the t had to be rational in Siegel's lemma. So you're going to have a linear factor to this as a polynomial in t. And that happens for at most finitely many y's and s. So that's how this lemma is a value here. It's not a really easy lemma to prove, but you can see it's simpler than what we started with, which was a polynomial x and y and trying to say when it factors. Here we're just trying to say when this polynomial in x and y has a linear factor. So it's a lot simpler. So this lemma 1 was something we had to show. And I won't talk about lemma 2, but say what it is in the context of this last slide here, really. This is another variation of what we did in terms of varieties, but again, it's just a system of equations and you're looking at when they're 0, so like our remainder coefficients. And if you, one important property they had that was sort of hidden in this discussion is that for each y0 and c, there were finitely many points, choices for the h0s, that's complexes, where this is inside this variety here. But that did happen for our setup, though it wasn't necessarily obvious. So suppose that we have infinitely many points where y0 is an s. Then it turns out, and this is what the second lemma was basically saying, is that we can actually find polynomial expressions for the y's, for the h's that we can plug in for solutions here. So the solutions are basically coming, well, this is going to be an infinite set. You can find polynomials in y's for the h's where this becomes an infinite set of points in this variety here. So things with, well, these are integers. When we plug in y0 being an integer and y0 is an s here. So you can find the infinite set's going to include points like this. Now that sounds almost like it would contradict because now we're finding infinitely many points. But what actually happens is that if you plug in these polynomials in y into the h sub k we were talking about that we were dividing by this polynomial of degree k, these are the coefficients, and you plug in those polynomials in y for your coefficients for this h, that h actually has to divide f of xy. So that would mean that f of xy, our original polynomial, had a polynomial divisor in terms of x and y, this h, and since f of xy is assumed to be irreducible when we started with, that would give us a contradiction. So this case where you have infinitely many solutions isn't coming up because if you have infinitely many solutions, that means our f of xy that we started with had to be reducible, had to be divisible by the kth degree polynomial. So that's basically all I wanted to talk about, except for I do have that slide.
Okay, thank you very much. So any questions from others? So is there any questions for Michael?
So here, can I ask?
Yeah,
sure.
Please go ahead.
Yeah. So here, density one is when we say dense subset, that means probability or proportion is 1.
Correct. So you bound the x's you're talking about, say, and count the number of x's inside that bound, and then let that bound go into infinity, and you get a density.
Right. Yeah. So are there alternative notions of density inside Z? Subsets, dense subsets of Z, or Zn?
Yeah, people talk about Zariski density, Zariski dense sets for the rational choices for these, and I don't really have a full grasp of that because that's not something I think about.
My curiosity is about, in this work, any other density will be also relevant.
Yeah. The other density, I don't know if people have looked at other densities with this.
Okay, thank you. And what is the role of genus? You're considering curves with.
Well, if the genus is greater than I mean, then you can use Siegel's lemma directly if the genus is greater than or equal to 1, and get information. If our initial polynomial f of x, y has genus greater than or equal to 1, then you can go ahead immediately and say there's finitely many points, integer points on it. So but that doesn't, what's kind of interesting to me is that that's talking about integer points. So really what you're talking about is finding choices for y0 where you have a linear factor because you want x to be an integer. So you plug in y0, you're getting f of x, y0. And if you want x also to be an integer, you're talking about a linear factor for that. So Siegel's lemma is saying something about integer points on this original f of x, y. And somehow that tells you you can use that to prove that there's actually not a factor of any degree for finitely many y0. Well, I shouldn't say finitely many y0, it depends. But the curves you end up with really are coming from either the resultant or by looking at these resolvents for the Galois group question. And you get in these curves, and if any of them have genus greater than or equal to 1, then there's going to be finitely many points. So you suddenly don't have to worry about showing there's finitely many points in S because there's finitely many integer points.
Okay, thank you. Thanks a lot.
So any other questions? Yeah, Michael, so here, I wanted to ask about this. Yeah, if you have an effect, like of course Siegel's lemma is ineffective, but suppose if you have a good effective bound on Siegel's lemma, like can you get something better, like the set S? Can you get some like S with better density, density S closer to 1?
I mean, you mean a smaller estimate than x over log x to the delta?
Yeah.
For the things not in S. I don't know how one would approach showing a smaller density. The nice things about this, if you have two universal Hilbert sets, their union is going to be a universal Hilbert set. So you can get more things inside. And I haven't looked at, necessarily what other approaches have done, and then if it would make sense to try to do that, but I suspect not. I mean, I think, I don't know how to improve on the x over log x delta.
Okay, thank you. So are there any more questions? Okay, if not, please
Michael.
Unmute. Yeah, Pradipto, yeah, I think, yes.
Peter.
Michael, hi.
Hi.
Yeah, so do things become more complicated if you look at the number field version of this particular problem? Is it? Yeah.
I don't know. I think most of the a lot of results are done in that generality. I mean, I don't think that. I certainly did not.
I see.
Yeah, I'm not sure what happens in terms of universal Hilbert sets but the results I was saying about Hilbert's irreducibility theorem has definitely been done in general, and that generality. The universal Hilbert set, I'm not sure to what extent that has been looked at in more generality.
I see. Thank you.
Mute all, please unmute all, and then let's clap for Michael, so for his nice talk.
It's a nice talk.
Okay, thank you very much, Michael.
Thank you again for inviting me.